Okay, so our last set of notes is basically on kind of what I was just describing. I need you guys to be able to apply a lot of these principles we've learned about electricity and magnetism. And I mean, we've only done 6 lessons up till now. There's not really a ton that you have to know. I mean, there's a few formulas obviously that you have to be familiar with, but I'd hope you guys would agree with me that other than recognizing like which one is E and which one is E with a line over top of it for like electric field strength versus energy, being able to recognize which scenario to use which formula, because one of the magnetic force formulas is for a wire which has a length of L, and the other one is for a particle which has a speed of V. Right? Like, so long as you can figure out where to use the formulas, they're probably not the hardest ones in the world. Like, compared to kinematics and dynamics, it's probably a lot easier. Hopefully you hear that. So anyways, my point here is I need to help you guys with a lot of the applications of this stuff, because I feel like in terms of what I've learned, you're going to get assessed on that. So let me give you a scenario just to start here then. So I mean, this could be a question you're asked to solve. Imagine that you have a scale, and the scale is created by having a current carrying wire sit in a magnetic field. Okay, so right off the bat here, I've got a bit of a picture here. This is a wire right here, and it is sitting in a magnetic field. Which way is that magnetic field going? What does X's mean? Good. X's mean it's going into the page. The way I like to use an analogy for that was the arrow. So like the back end of the arrow, where like the quill? Sean, you corrected me last day. Quill is the back of the arrow. Is like an X, and then if it was coming towards you, it would be like a dot. So this is going into the page, and then there's current running through this wire here. And using the third rule we learned last week, there's actually going to be a magnetic force pointing up. How would you orientate your hand to make that work? Okay, so the way that third left-hand rule works is your fingers point in the direction of the field. So your fingers have to point into the page. That make sense? Then your palm points the direction of the magnetic force. And so the magnetic force in this diagram is going to have to go up. So then which way does the current have to run? To the left. Yes, I'd agree. So that might be like the first part of a diploma question, is they might ask you, which way does the current need to run? And you would say electrons need to flow that way. Does that work so far? Okay. What they then continue to say here is if there's no mass sitting on the scale, the wire is at like equilibrium. But as soon as you place a mass on the scale, this gets pushed down. And then in order for it not to keep falling down and down and down and down, you have to add more current, because the more current you add, the more magnetic force it pushes back up. Does that make sense? So we have two forces that have to equal each other. We have to have gravity equal a magnetic force. Okay, then it gives me a whole ton of information here. And it ultimately asks me to find the mass of an object on the scale. So I kind of made these two formulas equal each other. Gravity equal magnetic force. What's the formula for gravity? Mass times 981, yeah. Well, now I need to make that equal to a magnetic force. I have two choices. Which formula is the right one?
The one with the wire.
Okay, so that one is, I believe, the current times the length times the magnetic field strength. And that one formula looks really funny, right? Because I wrote it with a capital I and like a curly L, but I think it writes it like as I-B. Like it almost looks like that. Which is really confusing because one is current and one is length. All right, how do you get mass by itself? Divide out gravity. So if we want to solve this for mass, we're going to need to know the current, which is given with 78 milliamps. We're going to need to convert it to just a regular amp. So what's that in regular amps? That'll work. So you can go 78 times 10 to the negative 3. Or you could call it just 0.078. That'll work. Then we need the length of the wire. 30 centimeters. Sure, 0.3. And we need to know the strength of the field, which was a millitesla. So again, a milli is like times 10 to the minus 3. And then lastly, I need to divide by gravity, which is, unless we're not on Earth, 9.81. What'd you get, Rush? Yeah, me too. It looks like I only get 2 sig digs, so yeah. 8.9 times 10 to the negative 6 units?
Total?
Yeah. So, I mean, just for some perspective, that would be 0.1, 2, 3, 4, 5, that many kilograms. That being said, do our scales normally weigh things in kilograms? They probably weigh them in grams. So, I mean, if this was a scale, you'd probably hack off 3 zeros and make it 0.0089 grams. So, based on that information there, was this mass particularly heavy? I guess no. I just made up random numbers, by the way. So I just picked some numbers that seem logical. Does that make sense, though, as like an application question? Where, like, I would suggest the math itself is probably not all that hard. You know, once you wrap your head around it, but that's the first key. Like, are you able to wrap your head around the scenario that you're being given? So. Questions?
So what was a left-hand rule?
The left-hand rule is for negatives for electron current, whereas we use a right-hand rule if we're somehow talking about like positive charges moving. So therefore, just one more time, you'd point your fingers into the page. Your thumb points the direction the electrons would go, and that would cause a force to go upwards, which would then counterbalance a gravity, which would be trying to pull you down.
Why would you use the first rule?
If for some reason we were talking about either conventional current, which is the direction protons would move, even though they don't actually move, or sometimes if you had, like, say, a proton flying through a field or something like that, like positives were moving, then you use your right hand. So, positive, negative.
If that arrow, that red arrow was facing up, would we not have known whether it was like?
This one right here?
Yeah, like how did we know it was this and not that without the arrow?
I think hopefully logic would dictate that gravity is going to pull you down. So then we're going to need to have like a force, something to keep from continually falling down.
Yeah.
Makes sense. That's the application part of it, is being able to recognize how to fit this together. I just left that slide blank for work. Okay, just want to do a little bit of a review just of the last class. There were 3 main rules I needed you to know. We used one of them already, that third left-hand rule. Let me remind you of the other ones. The first one was Oersted's experiment. If you have like I'm holding my hand here, so I'm using my left hand. If you have a current running through a wire, which would be this one right here, the current is actually going to induce a magnetic field in circles around your wire. Okay? And so if your wire goes this way, your fields are actually going to be in this plane right here, perpendicular to it. And so that's the first left-hand rule. If I were to put a compass right here, it would be pointing like, say, this way. Well, it's probably better to describe it as it would be pointing like out of the screen at us. If you guys can visualize that. If you were to have a compass down here, though, the compass would be pointing like into this screen. Does that make sense? So that was the first rule. The second rule is about, we often use the term solenoid. And it's where you have like wrapped coils going around and around in circles. There's 2 of them behind Sam on the desk over there. One is red, one is yellow. That's a basic solenoid. You wrap a whole ton of wires just in a big circle there. And what happens is it makes more or less it makes an electromagnet if you put some sort of metal in the middle there. The rule for this guy here is that whichever way the electrons are flowing is like the your fingers. That makes sense? So if the electrons are flowing this way, then your finger points towards the North Pole. And then the third one is the one we just did. The third left-hand rule is about either like a positive or a negative charge, so negative charge for your left hand. If the field means you're pointing towards south, and then your thumb is the like electron coming like towards us, then it would get deflected down. Make sense? Whereas for the proton would be me pointing towards the south magnet. The charge would be going this way with my thumb, so a proton would get deflected up. You guys remember those rules? Okay. Basically, I'm going to walk you through a whole bunch of famous experiments that hopefully, well, not hopefully, I hope they won't test you on them, but in case they do, we'll have talked about them at least. Like I said, I'm going to be really thorough. So, one guy I want you to know about, Ampere, which we actually named current after Ampere, because we call current like in amps. He discovered something. He discovered that if you have multiple wires sitting next to each other, and there's current running through them, they're either going to attract each other or repel each other. And I've got a diagram here that'll hopefully make sense. Let's say that this right here is a wire. Again, what does X mean? Okay, going into the page. So I'm going to use my left hand and point my thumb into the page. See how my fingers are wrapping around this way? It means that I'm inducing a magnetic field that's going counterclockwise. Does that work? And if I put another wire directly next to it, so two wires going into the page, what's going to happen is over here, this will be the north and south end of a magnet. Whereas around this side right here, which would have been like, say, this guy over here, this would be north, south right here. What's going to happen between these two magnetic fields? Well, north would attract south and south would attract north. What's going to happen to the wires? Yeah, they're actually going to come stick together, basically. There's going to be an interaction between them. Whereas, what happens if you have a wire going into the page, and this would be a wire coming out of the page? So, one more time. Going into the page, point your thumb into the page. Everything's going to go counterclockwise. Then point your thumb out of the page. It's going to go clockwise. So hopefully you can see how this works. Here the north-south and the north-south would actually match up with each other. So these guys would repel each other. Why is this important? Okay, well, think modern technology. Do we ever just have one wire running anymore? Usually we have many wires running together in a bundle. The one example that I read about was airplanes. They said that's probably one of the most common things you got to be careful on. You got all of these circuits running all the way through the airplane, and you're going to have some wires that are going to attract each other and some that are going to repel. So you have to be kind of careful here, because you don't want to screw up an airplane in the middle of flight, right? And I mean, I don't think an airplane is like the only example you could think of, right? Like pretty much any device that has many wires and they're going to be running next to each other, you have to at least factor in whether or not those wires will either be attracted or repelled, right? So, Ampere discovered there were three main factors that influenced how much attraction or repulsion there was. One was the length of the wires. That hopefully makes sense. The distance between the wires. So I mean, if there's one wire right here and another wire way over here, it's probably not as big a deal as if there's one wire right here and another wire right directly next to it. You know what I mean? And last one is how much current is flowing through the wires. Oh, you guys remember what current is again? That's a good way of putting it. Yeah, it's the amount of charge per time. I like to think of it as how fast they're moving. Right? Like it's how many particles will pass in a second. So, based on what I've read, you don't actually have to calculate force on this by any means. You just need to know whether wires will attract or repel. So if they give you some sort of diagram, you might be asked a theory question and say, what will happen to these two wires? And you'd say, well, these ones would come together and these ones would push apart. Does that make sense? There's one application. Another application is a generic motor. Motors are actually a fantastic example of electromagnetic principles, I guess. Okay. Let's see whether this diagram makes sense right off the bat. Maybe I'll use the different one though. Let's use this one here first. This one I think is labeled a little better, so maybe head to the bottom one. Imagine that what you've got going on here is a magnetic field between a north-south magnet, well, two different magnets, I guess, right? Because you can't just have a north half and a south half, right? So, and what you're going to do is you're going to put like a looped wire in between them. And then you're going to put electrons going through the wire, just like this one shows here. Let's focus on just this section right here first. If the electrons are going this way, so I'm going to point my thumb that way, but my fingers have to point in the direction of the magnetic field. Which way do my fingers point then? Towards the south. So I need my hand to be kind of like this, where my fingers are going this way. South is this way. Which way is the force going to happen in this particular section of the wire? Up. Yeah, I'd say the force would be going up. But then that exact same wire flipped around, coming back the other way. So now, still pointing my fingers towards south. My thumb is going in towards my body now. Now the force is going down. Does that make sense? So what would happen if someone pulled this part of the wire up while simultaneously somebody else pulled this part of the wire down? You'd have like a torque, you'd have a rotation. Does that make sense? Well, if you could keep that rotation going around in circles for forever, that's basically a motor. What does a motor do? Spins. It basically creates motion from electricity, right? Basically, do I have this written anywhere? A motor will take electricity and create motion. Does that make sense? And this is basically the principle about how it does it. You throw a current inside a magnetic field, and it causes this thing to rotate. This particular diagram labeled the electron flow, but let's say it didn't label this electron flow. How could we tell which way the electrons were flowing? Battery, yeah. The battery is going from negative to positive. For you guys in my grade 12 class, we're talking about this in electrochem, so I want to use this terminology. Grade 11s, you don't probably need to know this for your diploma, but I think it's worth mentioning. The negative side of a battery is called an anode, and the positive side of a battery is called a cathode. Here's an easy way to remember that. Anions are negative, cations are positive, so hence anode and cathode. It's the proper terminology to use when talking about a battery. I don't think you need to know this for this course, but it's probably worth talking about. Yeah, because you guys will be using it in grade 12 chemistry all the time. So electrons flow away from anodes and towards cathodes. So going back to this diagram here, there's three main parts of this motor that I don't think you're going to get tested on it, but like I said, I want to make sure I'm covering everything just in case, because I really don't know what they're going to throw at you in terms of the applications of this stuff. So, three main things. First, I don't even know if I'm saying it right. The stator, I don't know. There's a magnet. You need a magnet as part of this thing here. Chances are there could be like another half of a pole over here where this is the south pole or this is the north pole over here, or it's like a big horseshoe magnet. You guys know how you can have like a horseshoe magnet instead? So you need a permanent magnet basically sitting in there somewhere. That's one part. The armature is basically this coiled wire. It's going right here. And then there's one more thing you need. It's called a commutator ring. And I think I have a diagram here trying to explain how the commutator ring works on one of my next slides. So let me see that I can find that. Why didn't put the diagram in? Why didn't I put the diagram in? Well, let me draw what the diagram would have been, hopefully. Shoot, I should have included that. Okay, well, let's see whether I can just zoom in on this photo here. So this thing right here is the commutator ring. So let me just try to draw this a little bit closer. I'm going to have a wire coming in, another wire coming in, and then basically this thing is like two different halves of like a circle, only the circle doesn't fully touch. And what's going to happen is this guy right here is then going to go around that little loop there and come back. Okay. What's going to happen here is as the force causes this guy to rotate, eventually this guy will be to the point where it's like right here and right here. Does that make sense? And what we've done is we've caused this thing to rotate about as far as it can get. But as soon as it's done rotating and getting all the way to that point, it would just stay there. And what we need to have it do then is flip a second time. Am I describing this very well? You've got your hand like say like this, and you've managed to force your thumb up and your finger down. And so now you're to this point here. Well, how do I keep it going? How do I get it to keep going like this? And then like this? And so on. Does that make sense? So I mean, it's easy to get my hand to go from here to here. Right? How do I keep it going? And so the idea would be then is there's like a brief second in time where it would look kind of like this, where no one's actually in contact with each other. But like your inertia, like your momentum, is going to cause it to keep rotating. And so what happens is its momentum keeps, by the way, we're rotating like this way, in case my diagram doesn't make sense. And so for a brief second in time here, these things won't be in contact with each other. Momentum carries it so that then this one will then start touching this way, this one will then start touching this way, and then the same thing can happen. Well, now it'll force this guy up, and it'll force this guy down. Does that make sense at all? So the basic idea is in order to keep it actually spinning, there has to be like a little break in this thing here so that you can have half of it turn, momentum keeps going, re-picks up, keeps turning another half turn, momentum keeps going, and it can keep spinning continuously in circles. So anyways, you should know the concept of a commutator ring in case they quiz you on it. Basically, it's required to have like a split down the middle so that it can continue going in circles. So. I guess just I've got lots of pictures here. Hello. You okay? What happened? Oh man. Okay. Another thing you may be asked about in terms of applications is something called a galvanometer. Okay. Galvanometers work on very similar designs. Yeah. You guys ever heard the term galvanometer? Basically, it's any sort of device that has like a needle reading that kind of moves upwards. So the best example I would give is like a voltmeter, because we're going to use those tomorrow. Those are like those little meters that are sitting beside Sam on the counter back there, like the red and black ones. Basically, what happens is a needle is going to move. Does that make sense? Well, it's kind of a similar concept to the motor. Here's the thing, though: it's not going in a continuous cycle. Okay. All you want to do is you want to force, like you want to have a force that goes up here and a force that goes down here that causes the needle to move, but we're not intending for the needle to go around in circles like a motor. We just want a needle to go just a certain direction. And so what we do is we attach it to a spring. Because what will happen is the spring will try to keep the needle from going all the way there. It'll like, you're trying to force it up. Does that make sense? And based on how far it manages to move, depends on how far your meter shows. Like along the edges here. Does that make sense? Oh, one of the big differences then between a galvanometer and a motor is this whole little split ring commutator thing is not necessary, because the point of this thing is to make it continually go around in circles, and we don't need this thing to go around in circles. So, I actually have a question to try on this. So. Let's say you have a galvanometer and it has a length of wire next to each pole. So like this guy right here is 3.8 centimeters and this guy right here is 3.8 centimeters. And then we put it inside a magnetic field and we run a current through it. And so I'm even going to show you the direction of the current. The current is going this way. What's going to happen to this, like, make sense? Well, let's try one head at a time. If the field is going, let's say, from north to south, and then the electrons are going up, which way is the force going to be? Towards us. So that's why this right here, this yellow, is intending to mean that like this part of the ring is going to come towards us. That makes sense? Whereas then this part of the ring is going in. So basically it's going to spin like this. You can picture that. Is it actually going to spin though continuously? It's just going to move, right? And so my question basically is, well, let's try to figure out what forces are equal to each other. You're going to have a magnetic force. What is restraining this thing though? I heard it. Yeah, the spring is trying to restrain it. So we're going to need to have a magnetic force equal a spring force. Makes sense? Because otherwise this thing would rotate freely. A spring is going to try to pull it backwards. And however far the spring is able to move is how far like the needle on one of those devices moves. So, formula for magnetic force?
This is the wire one again?
Well, it's still a wire, yeah. So
Current.
current times length times field strength. What about formula for like a spring?
Is it
That'll work. There is a negative on that, but why do we have that negative again? You guys remember? Yeah, exactly, right? So we don't really need the negative for our calculations here. Let's find amps. So that's I. So we need to divide by L and B. Need to divide by L and B. So the amount of current running through this thing must be equal to the spring constant. So 87.6 newtons per meter times by how far the actual spring moves. Do we have that anywhere? Yeah, it's that 3.5 millimeters. So that'll be like 3.5 times 10 to the minus 3 meters. And then we need to divide by the length of the wire. I'll be really careful on this one. The length of the wire was 3.8 right here.
Oh, but it's,
And it's doubled though. And one of the reasons why it's doubled is that this guy is being forced out of the page, but this one is being forced into the page. So really you get double the amount of force. That make sense? So at the very least, maybe the easiest way of solving this is let's double the amount of wire. In terms of how much wire is actually perpendicular, like this wire right here, not relevant, because it's not in the right direction. But this wire and this wire are both in the right direction, so you're gonna have, what, 7.6 centimeters? And then magnetic field strength was 1.25. So I've got 3.2 amps. Well, that's basically what one of those devices does. It either measures, like, say, voltage or current or something like that. And so, based on all of this information, the little needle would be pointing at, like, 3.2. That's how far the spring is going to allow it to move. Does that make sense? So, again, I would say math is not necessarily all that hard, but figuring out what forces to make equal to each other is probably a little more tricky. And being able to interpret some sort of big diploma level question is, like I said, that's probably the hardest part, is the interpretation. Questions? No. Okay, another guy I want you to know more about. Michael Faraday. You might have maybe heard his name come up before here. He discovered, or at least is credited with discovering electromagnetic induction. Let me just read off of here. In the 1820s, pretty much all of our research into magnetism and electricity, from what I understand, happened over the course of just over 10 years. Like in the 1820s to the early 1830s, pretty much everything was discovered all at once. People started working on this. Beforehand, they really weren't working on it, and afterwards, they kind of figured most of the stuff out. So in 1931, Faraday discovered electromagnetic induction. His thought was, if you can have moving electrons create a force using a magnetic field, maybe you could go backwards. Maybe you could use a magnetic field and a force and maybe cause electricity to form. Does that make sense? So rather than electricity and magnets causing a force, what if you used a force? Could you make electricity? And that's actually what basically a generator does. We can actually create electricity. And so he discovered electromagnetic induction using this apparatus right here. So let me try to describe to you what he did. he had hoped that if he turned on the battery right here, what would happen is that the ammeter over here would actually like register that there was current. That's what he was hoping for. And he discovered though that when he closed the switch right here, the ammeter did not register any current. He'd be like, oh, well, why didn't it? So he was hoping for that. He didn't discover that, but he discovered something else. As he turned on and off the switch, the little needle on the ammeter flickered just for a second as he turned it on and as he turned it off, which he thought was strange because, well, why when I turn on the switch does the little needle, you know, that makes sense. Why does the little needle move only when I turn the system on and off? So here's what was happening. What happens right here when you turn on the current? You're creating a solenoid, right? That makes sense, like the looped wire. Yes, that's what happened. Is it created a magnet? It created an electromagnet here, where well, I'll just make up some numbers here. Hypothetically, let's say this was the north-south end of a magnet right here. Okay. That's what it created. Well, what is this north-south of a magnet going to do directly next to another solenoid? It's going to induce like a south-north end of a magnet over here. And as soon as it induced a magnet over here, it caused it to then have a little bit of a reading on the ammeter. Let me just read my notes here. This apparatus was creating an electromagnet right here, which then induced a magnetic field. The first electromagnet induced a magnetic field in the second electromagnetic. And then what happened is because there was an electromagnet right here, that actually caused, for a brief moment in time, the ammeter to register some current moving. And so we have a term for this. We say that current was induced. And we can induce a current whenever we have moving electrons or when we have moving magnets. Probably the best example I can give of this, has anyone ever seen those flashlights where either you like turn a crank or you shake them? You ever seen these before? Obviously you've seen or heard of them before, right? What's happening is you're moving a magnet within a coil, and as you move it back and forth, the motion causes the electrons to move. Like the motion of the magnet forces the electrons around the wire, which is kind of backwards. Normally, moving electrons and a magnet cause a force. Here, your force and the magnet will cause the electrons to move. Here's a really typical demonstration that you guys are going to do tomorrow. Take like a basic curled wire and move the magnet in. As you move the magnet in, it's going to force the electrons through the wire, but only when you're moving it. Okay. So like let's say you take the bar magnet and you put it inside the wire. The little needle on the ammeter will flicker only as you're moving this thing in. As soon as the magnet is just sitting there, nothing will happen. And then you pull the magnet back out, motion will cause electrons to move just for a second. So if you move it in and out and in and out and back and forth consistently, you're going to create a lot of current. You guys ever heard of like alternating current? I believe this is actually one of the principles behind it, because what you're doing is you're causing the electrons to go one way and then the other way and then this way and then the other way. And so you're going to have electron flow, but the electrons are alternating which way they're going based on whether the magnet is either going into the coils or out of the coils. So long story short, he discovered you can create electricity. What was I going for in this diagram here now? Forgot. Oh, okay. Imagine that you've got a wire right here, and the wire is hooked up to a loop. And you take that wire and you move it in a magnetic field. Here's how you can figure out how the electrons work. It's just like that third left-hand law. Okay. Your fingers are going to always point in the direction of the magnetic field, so your fingers would point towards south. Let's say that then your wire, you physically take the wire and you move the wire up. Or you take the magnets and move them down. I don't really care who moves, but someone has to move relative to each other. But let's assume that like the wire itself is moving up. So basically my hand would look like this over to the screen. The force now is not going to be the force on the wire, it's going to be the force inside the wire, causing the electrons to move. And so electrons will be forced towards us. And so then current would run this way if you were to move the wire up. What would happen then if you move the wire down? The electrons would just go the other way. And so if you just had a couple of magnets sitting there and you moved a wire up and down inside the magnets, you'd actually be causing electricity. Hey guys.
There's two strings.
I see G-strings. I have an error on here right now. I just lost these guys. Why don't you guys go take a 5-minute break? See if I can get them back. It's already been a while. Okay, so yeah, basically, test question for you guys. Let's say that the wire is pushed down. Now, by the way, the wire itself doesn't have to get pushed down. You could move the magnet up. Does that make sense? It doesn't actually matter who moves, wire down or magnet up. So let's see. The actual field is going into the page. The wire is getting pushed down.
What? Why'd you do that?
Because my finger is the direction of the motion. So into the page are my fingers. Like I said, you can tell when someone's doing this unit because they're trying to contort their hand, right? So into the page, the wire is getting pushed down. Which way is the electrons being forced? They're being forced your palm. So electricity would be going
It's different for every.
this way.
I thought, like, in the third hand rule that your thumb is the direction of the...
Well, your thumb is the direction of motion. And then your palm is the direction of a force. So in this case here, since the motion is you moving the wire, your thumb is going to be the wire this time. Whereas like if it was just like an electron flowing through a field, then your thumb would be the electron and your palm would be the way that the electron is forced. So force, motion, field. So one more time. Into the page is your fingers. Thumb pointing down because that's the motion, like the direction it's like velocity, I guess, would work. And then your palm is the direction of the force, meaning we are going to force these electrons. Force, or we use the word induce. We're going to induce the electrons to go that way. We're going to force them to go that way. Normally they wouldn't do anything, they just sit there. But because we're moving a wire in a magnetic field, it causes electricity basically. So, left. Does that work? No. Okay, in 1930s as well, this is the last guy I need you to know about, Lentz. He basically concluded that he should be able to figure out two different possibilities for the like a pole as like magnets moved through a coil. First, I want to show you his incorrect thought process. Let's imagine that you took a south-north magnet and you tried to force the magnet inside a coil of wire. Which way are the electrons going to go? The electrons could either go like up around the loop like this, or they could go down around the loop here. And so what he thought is, well, what happens if this north-south magnet induces a south-north magnet? But that was actually incorrect. That's not the way that this actually works. What ends up happening is a south-north magnet will actually induce a north-south magnet here. It kind of has to do with energy and work. What's going to happen here is because you're pushing this guy in this direction right here, it's the solenoid needs to try to push back at you. Does that make sense? So if like, you know how like Newton's third law is for every action there's an equal and opposite reaction? If this guy is being pushed in this way, in order for the electrons to move, it's almost as though this one needs to try to attempt to push back at you. But instead of being able to push back, the electrons move instead. So if this is the correct orientation then, you guys remember the curled up left-hand rule? Okay. If my thumb is pointing towards north, then the electrons are going to be going like this. So they'll be coming over the top of the solenoid. So that's why the electrons are going over the top, like this. So up the back side and around the front side. Make sense? Whereas in this particular one right here, if you were pointing your thumb that way right there, it does make sense. But this is not the way the poles of your magnet would work.
So what is the thumb again?
So in this one here, the thumb is the direction of the north side of the magnet that would be hypothetically produced, like the electromagnet. And then your fingers are the direction the electrons would curl. Okay. Think Newton's third law, though. This right here is not going to induce a south pole, is what Lenz discovered. It's actually going to induce a north pole. It sounds weird, because you normally think north attracts south, right? But we're not looking for an attraction here. We're actually looking for like an equal and opposite reaction. If you force a north pole to go this way, it's going to want to force a north pole to go back way, but it can't actually create a north pole. So what happens instead is the electrons move. And so the electrons are going to move as though the north pole is on this side right here. Let me try another example. Where is that example? Here it is. So here's an example. Let's try to figure out which way the electrons would move if you were to take a magnet and pull it out of a solenoid. So what's going to happen here? What sort of pole will be induced right here? A north or a south pole? Yes, a south pole. Why a south pole? Well, you're pulling it away. Okay? If you're going to want to cause electrons to move, you need like an equal and opposite reaction. And so is a north and a south pole really going to want to separate from each other when you pull it away? Does that make sense? So like the basic idea would be here, if you're pushing it in, it's going to induce the same pole because it's going to induce something that's going to be like an opposite of what you want. And that opposite force then causes the electrons to move around. Here you're pulling it away. Now, we don't want it to be like a north pole right here because then, I mean, north and north would already push each other away, and we don't want that. We want a south here so that there's actually like an attraction between those two, that when you actually pull it away, it causes the electrons to then move. So then if this is a north and this is a south pole, I lost those guys again. We'll just finish off here. If that's the south and that's the north pole, point your thumb towards the north pole. The electrons will then come up the front and go around the back side. So then the electrons would be going that way. Right.
So if the magnet was going into the coil, would it like put the current around that?
Yes. That's basically the AC concept. Is if it's going in, it's going to cause the current to go one direction. As you pull it out, it causes the current to go the other direction. Yeah. Okay, anyways, take a second, read this slide here while I try to get these guys going back here. I just need you to know the basic concept of what Lenz's law is. I like to think of Newton's third law myself. Everything is going to have an equal and opposite reaction. Basically, that's what his law says, is the induced current is going to have to be such that it opposes the cause of the current. So if the magnet's north end is going into the magnet, it's going to have to like pretend as though the solenoid had a north end going towards it, so that the two norths would ideally repel each other. But I mean, since they won't actually repel each other because one of them is not actually a magnet, what will happen instead is it'll force the electrons through the wire. But if you pulled it out, it would actually cause the electrons to go the other way, like I was mentioning to Brad a few minutes ago. Hence the whole AC/DC concept, where alternating current, the electrons will go this way, and then back this way, and then this way, and then back this way, and it fluctuates back and forth, basically. Does that make sense? There's a lot of memorization of like principles. Probably the biggest key though is trying to be able to apply them to whatever scenario you get. Was that my last slide? Okay, so they didn't really miss much. My computer's kind of screwed up. So, Okay, I'll call it there for the lesson. Let me just pause the video here.